Most chemical reactions appear to go in one direction. However, many reactions can run both forwards and backwards, reaching a dynamic state of balance called equilibrium. This video will explore reversible reactions, how systems reach equilibrium, and how conditions can shift that balance. Our roadmap covers 4 main areas: reversible reactions, understanding dynamic equilibrium, Le Chatelier's principle, and required practical applications. This topic builds directly on your understanding of reaction rates. A reversible reaction allows products to reform the original reactants, proceeding in both the forward and reverse directions. We represent this using the double half-arrow symbol. For instance, heating solid ammonium chloride produces ammonia and hydrogen chloride gases. Cooling reverses the reaction, reforming the solid. Precision in language is essential when discussing these concepts. The forward reaction goes left to right, while the reverse reaction goes right to left. Remember, if the forward reaction is exothermic, the reverse must be endothermic by the same energy amount. Only use the double half-arrow for genuinely reversible reactions. Dynamic equilibrium occurs when a reversible reaction takes place in a closed system. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Concentrations remain constant, but are not necessarily equal. Equilibrium is dynamic, meaning both reactions are still constantly occurring, not static. Dynamic equilibrium requires 2 specific conditions. First, the reaction must occur in a closed system so no substances can escape. Second, the reaction itself must be reversible under the conditions present. If the reverse reaction is negligible, equilibrium cannot be established. Le Chatelier's principle is the guiding rule for predicting how a system at equilibrium responds to change. It states that the equilibrium position will shift to oppose the change, minimizing the disturbance. The 3 main changes we consider are temperature, pressure, and concentration. Temperature is the only factor that changes the value of the equilibrium constant, Kc. Increasing the temperature favors the endothermic direction, which absorbs heat. Decreasing the temperature favors the exothermic direction, which releases heat. A catalyst speeds up both reactions equally and does not shift the equilibrium position. Pressure changes only affect equilibria involving gases. Increasing pressure shifts the system towards the side with fewer moles of gas to reduce the pressure. Decreasing pressure shifts the system towards the side with more moles of gas. Solids and liquids are excluded from this consideration. Changing concentration is an intuitive application of Le Chatelier's principle. Adding a reactant shifts equilibrium to the right, increasing product yield. Removing a product also shifts equilibrium to the right, a key industrial strategy. The reverse changes shift the equilibrium to the left. This table summarizes the effect of all factors on equilibrium. Note that only temperature changes the value of Kc. Pressure and concentration changes cause shifts in the equilibrium position, but do not alter the value of Kc. The Haber process, producing ammonia from nitrogen and hydrogen, is a classic industrial example. Maximum yield favors low temperature and high pressure. However, industrially, a compromise is used, typically around 450 degrees Celsius and 200 atmospheres, along with an iron catalyst to maintain economic viability. The contact process, producing sulfuric acid, is another key example. The forward reaction isexothermic. For maximum yield, lower temperature is favored, but 450 degrees Celsius is the industrial compromise. High pressure favors the product side, but a near-perfect yield is already achieved at atmospheric pressure, making higher pressure unnecessary. The equilibrium constant, Kc, relates the concentrations of products to reactants at equilibrium. A general reaction yields the expression Kc equals products over reactants, each raised to its stoichiometric coefficient. A large Kc means products are favored. A small Kc means reactants are favored. Remember, Kc's value is fixed at a given temperature. Here are 3 examples of writing and interpreting Kc expressions. In the Haber process, Kc has units of mole squared dm to the power of 6. In the hydrogen iodide formation, moles cancel, so Kc has no units. For esterification, all species are included as they are not pure liquids or solids.